Hello, welcome to Understanding Power Electronics. When an AC motor or an AC transformer is switched on, we know that an inrush current will flow. Electrical engineers know that you have to reduce this inrush current and also mitigate the effects due to the inrush current. Likewise, a boost converter, when it is switched on, an inrush current flows, and this inrush current can create potential problems. In this video, we will see how this inrush current arises in a boost converter, what can be the problem due to this inrush current. We will also look at a few ways to reduce the inrush current and mitigate the problem. That is our aim. Let's get started. We are aware of the inrush when there is a sale for a popular phone or a popular toy. What we are talking about is the inrush of current in a boost DC-DC converter. This is a boost DC-DC converter connected to the source Vin via some switch SW. Notice that even with the switch S turned off, the inductance L, the diode D, and the output side, the capacitor C and the load RL are all connected in a loop to the source Vin. So this is the cause of the inrush current, because when you connect the converter, there is a path for a current from the source to the output side via the inductor and the diode. Next, we will see the inrush current in greater detail. This is the boost converter and we are switching it on. We are connecting it to source Vin through some switch SW. The switch is shown to be a double pole switch, but it doesn't have to be. It can be a single pole switch with this zero potential or the ground potential permanently connected. In order to draw the waveforms and see what kind of inrush current arises, etc., let us give some values to these components. L is taken to be 0.2 millihenry, C is taken to be 50 microfarad, RL, the load resistance, is 50 ohms, Vin, the input voltage, is 180 volts DC, the switching frequency is assumed to be 40 kilohertz, and the duty cycle is taken as 0.4. Notice that in the DC-DC converter, we have taken the load to be a resistive load RL. It doesn't have to be. Most likely it won't be. But we are assuming a load resistance because it is easier to analyze and understand what's going on. The operation of this converter under these conditions, under steady state, can be shown to be in the CCM region or the continuous conduction mode region. In this region, the output voltage V0 is given by Vin by 1 minus D, which will be 180 volts divided by 1 minus 0.4, 300 volts. So the steady state output voltage under this operation is 300 volts. There are a few videos in this series which explain the operation of the boost converter under steady state in greater detail. You may wish to go through them in case you are not familiar with the operation of the boost converter. And with 50 ohms load, there will be a load current of 6 amperes. And we can also show using power balance that the input current will be 10 amperes. Now assume that we are starting this converter. We are not talking of the steady state operation of the converter. We are starting this converter. The switch is off. During this part of the discussion, we are not switching the switch at all. We are just connecting the source to the DC-DC converter. As I mentioned earlier, there is a path from the source to the load via the inductor and the diode. The initial current, we are just starting. The initial inductor current is 0. And likewise, the initial capacitor voltage is 0. So there will be a current that will flow in the circuit even when the switch is off. That is the particular feature of the boost converter and boost derived converters. So here, assuming ideal diode, there is an LCR circuit connected to Vin, and we can draw this circuit separately. We will assume that the values of L, C, RL, and Vin are the same as those of the boost converter. Now, this circuit, we can write the differential equation for it. I won't go through the process of obtaining the differential equation. If you have forgotten your calculus and do not remember how this differential equation comes about and how to solve it, it's okay. You will still be able to follow the main parts of this video. The initial inductor current is 0 amperes. The initial capacitor voltage is 0 volts. By applying KVL, L dIL by dt plus Vc is Vin. Initially, Vc0 is 0 volts. So IL dashed 0, the initial value of the derivative of the inductor current, IL dashed 0, is Vin by L. IL0 is 0, IL dashed 0 is Vin by L. You can solve this equation for these initial conditions using Laplace transform or by finding the homogeneous solution and the particular solution and then applying the initial condition. Either way, you will get this result. You can see you have e power lambda t cos mu t here, e power lambda t sin mu t here. Lambda is minus 1 by 2 RLC and mu is this. Lambda is a negative quantity. These two functions together form an exponentially decaying sinusoidal function. It is a sinusoidal waveform, but the amplitude is going down exponentially. That is e power lambda t. Likewise, you can find the equation for Vc, and the Vc equation is given by this. Again, the first term contains e power lambda t cos mu t. The second term contains e power lambda t sin mu t. This is also an exponentially decaying sinusoidal function. Under steady state, e power lambda t will tend to 0 as t goes to infinity. So the first two terms will go to 0. So IL will be Vin by RL and Vc will be Vin. The LRC circuit is given here. The values L, C, RL and Vin are also given here. And the steady state values of this circuit is Vc steady state is 180 volts and IL steady state is 3.6 amperes. We also use two parameters, lambda and mu. Lambda is a negative quantity, and if you calculate lambda substituting RL and C, we will get minus 200 second power minus 1. Mu we can calculate likewise. Mu is the angular frequency in radians per second, that is 9998 radians per second. So mu is almost equal to 1 over root of LC, which is the resonant frequency of an LC tank circuit. The presence of RL changes it slightly. We derive the equation for IL. It is given by this expression. Substituting for the values of V in RL, etc., and also lambda mu, we will get this equation for IL. Likewise, Vc equation is this, and substituting all the values, we will get Vc equals this. We can plot the IL and Vc waveform. The x-axis is time in millisecond, y-axis is amperes or volts, depending on whether we are plotting IL or Vc. If you consider IL, if you look at this, the cos term amplitude is quite small. Essentially, the sine part dominates. So basically, this waveform is an exponentially decaying sine wave shifted by 3.6 amperes. So we can plot it. This is the waveform and the steady state value will be 3.6 amperes. The load resistance RL is pretty large, so the damping provided by that is not very high. So the exponential decay is quite slow. Likewise, we can plot the Vc waveform. Here in the Vc waveform, you can note that the second term is negligible. The amplitude is only 0.020. The waveform is negative of an exponentially decaying cosine function shifted by the amplitude. So you can see that the waveform will have a wave shape as shown. The steady state value will be 180 volts, that is V in here. So this is the transient you can expect if you have an LC and RL circuit fed by V in with the values of the components being the same as that of the boost converter. Now I'm here. Now we will see how this LRC transient relates to the boost converter. If you look at the current waveform at around this point, around 0.32 millisecond, the current goes negative. In the actual boost converter, IL going negative means that the diode is conducting in the reverse direction. It cannot, so the diode will block it. So we can take this diode and put it here. When the current tries to go negative, the diode will block and the current will stop. Here is the simulated results of a boost converter startup using LT Spice, the link provided below. Notice that the simulated inductor current waveform of the boost converter is identical to that of the LRC transient waveform. The capacitor voltage also likewise is the same. At this time point, the capacitor is left with around twice the supply voltage, around 340, 350 volts, and the diode is off. So the capacitor will discharge into the load resistance and it will exponentially decay as shown. These are the simulated waveforms of the input current and the output capacitor voltage of a boost converter. Notice immediately that the inductor current or the input current reaches a very high value of 90 amperes. Remember that the startup steady state current when the switch is off is only 3.6 amperes. And also we saw a short while earlier that the input DC current at D equal to 0.4 under steady state was 10 amperes. So this current 90 amperes is 9 times more than the normal operating current. And it occurs for a reasonably long period because L and C are large values, they are filter components. So the period of oscillation is also pretty large. This is going to be half of that period. So a large inrush current, much more than the normal operating input current, occurs for a reasonable length of time. That is the problem. That is the issue here. Another thing is the voltage is going to 360 volts. It is twice the input voltage. Remember, it is a 180 volts amplitude cosine function shifted by 180 volts. So the peak will go close to 360 volts. As we calculated earlier, output DC voltage under steady state for D equal to 0.4 was 300 volts. So this is more than that. If the load is not able to take this higher voltage, then we will have a problem. But the main issue is this surge of current. We will next see what the problems are because of this high input surge current and how to reduce it. What we have seen so far is that when we turn on a boost converter, a large input inrush current will occur. So first problem you can expect is this high current can damage components, damage to PCB traces, damage to diode, etc. One has to be careful there. So in order to protect against this inrush current and also to protect against short circuit, overload current, etc., a fuse or a circuit breaker may be added in series as shown. This circuit breaker, this fuse may trip. Every time you start the boost converter, there is a likelihood that this fuse might trip. So that is the second problem, a nuisance tripping of the fuse circuit breaker, which may be used to protect the boost converter and the downstream load. The third problem is a bit more subtle. It is the input voltage dip that may be caused by this inrush current. We will see this in greater detail now. Why does this dip in the voltage occur? That's what we are going to see now. This is the boost converter fed by a DC voltage source. We are looking at the converter under startup conditions. The boost converter is represented by this box and it is fed by this V-in voltage source. So I'm showing the input current waveform and the capacitor voltage waveform here. And I'm also marking this voltage as the input voltage of the boost converter. Of course, in this case, V dashed in is the same as V in. So V dashed in will be 180 volts throughout. There is no dip in the voltage. So why would the dip occur? One reason V dashed in can dip is because of any inductance here. Between the source and the boost converter, there is going to be a wire connection or a PCB trace connection that will have some inductance, self-inductance of the wire or trace. Because of this di by dt of the input current, that inductance will drop some voltage. So V dashed in will be V in minus VLS. So we can expect some change in the V dashed in because of the line inductance, that is the wire inductance. But typically this inductance will be of the order of some nanohenries. The boost inductor L is effectively in series with this Ls, and boost inductor is likely to be much higher than this. So voltage dropped in Ls will be relatively small. So V dashed in may not change that significantly. You have to deal with this on a case by case basis, but in general, V dashed in is unlikely to change much due to the presence of the wire inductance. There is yet another reason. This V in may be a power electronic source itself. This power supply V in has some characteristics. As you load it with some current, the voltage remains constant at V in. That is the definition of a voltage source. This voltage source may have a current limit to protect itself and also to protect the boost converter and the load. If you try to draw current beyond this I limit value, the voltage of the source drops to maintain the current constant. So the power supply starts acting as a current source in this region. You might have noticed this in your laboratory power supply. What happens when such a source is used? We can do a simulation using again LT spice, and the current waveform is shown here. Initially, it just follows the IL waveform earlier. I limit is set at 30 amperes. At 30 amperes, the source switches to the current limit mode and maintains a constant current of 30 amperes. High surge of current is avoided. The output capacitor gets charged more slowly. So the current is limited to 30 amperes. It does not go to a high value of 90 amperes. Once the capacitor gets sufficiently charged, the current starts to fall. And as the current starts to fall, it is no longer limited. Source switches to operating as a normal voltage source. So if I plot the capacitor voltage waveform, you can notice that the voltage of the capacitor also does not reach a high value. The voltage also reaches only 230 volts also. It does not reach 360 volts. If you look at the V dashed in waveform, during this region, the current limit is not operating. The input voltage source is acting as an input voltage source. So the V dashed in will be 180 volts. Once the current limit kicks in, power supply drops the voltage to a low value so that the current limit is maintained. Then you have constant current flowing. Because the current is constant here, the capacitor voltage and the source voltage are the same. So the source voltage V dashed in follows the capacitor voltage until the source voltage reaches 180 volts. The source voltage cannot go higher than 180 volts and the power supply comes out of the current limit mode. Notice one thing now. The high surge current is avoided. So this is actually a very good method. You are avoiding the high surge current. In fact, even the voltage does not go high. So what is the problem? The problem can be that There may be other connected loads which are already operating, other electronic loads which are already operating. During this interval, the input voltage or the source voltage is limited by the current and it drops. For quite some time, it drops. So the voltage seen by the other connected loads has a dip. So this can be a potential problem. In other words, if you have connected loads and if your source is a current limited source, this can be a potential problem. Current limited source is very good for the boost converter itself. The current surge is prevented, but it can cause a voltage dip in the DC bus here, and that might affect other connected loads. To summarize, damage to the PCB traces, diode, etc., nuisance tripping, fuse blowout, and the third one, possibility of input voltage dip affecting other electronic loads, particularly when you have current limited source feeding the boost converter. Okay, a quick aside here. How about other converters? Will they also suffer from the same problem? Let's take a quick look. Let's take a buck converter. Similar discussion you can do with a buck boost converter also. So this shows a buck DC-DC converter and it is being fed by a voltage source with a switch. We are turning on the switch and the buck converter is operating. Notice that here there is no direct path to the load side. So there is no surge of current that will be flowing into the load side like here. In the boost converter, you have a direct path to the load via the inductor and the diode. Here you have a switch. You can start the converter slowly by keeping the duty cycle very small and slowly build it up. That's called soft start in order to build up the current and voltage on the output side slowly. So that's not an issue. In the case of boost converter, the switch is on the shunt path. In the case of buck converter, the switch is on the series path on the input side. So we have all the control we need to limit the current. If the current becomes too high, we can switch it off. We can switch off the switch, yes. But there is a problem. The problem is the input current in a buck converter is not smooth. Here in the boost converter, you have an inductor on the input side. So relatively the current will be smooth. In the buck converter, even under CCM, the inductor current will be smooth, but not the input current because input current flows only when the switch is conducting. So part of the period switch is conducting, part of the period diode is conducting. So the input current waveform will be a chopped waveform. And you're likely to have some inductance here because you're connecting the source to the buck converter. So you will have some wiring inductance LS. Now you see what the problem is. I'm having an inductor LS. It may be 20 nanohenry, 30 nanohenry. We have a series switch S, which is switching on and off at the switching frequency. Inductance current being interrupted by the switch will give rise to a large spike in the voltage. So the voltage at V dashed in will not be a nice DC voltage. So what do you need to do? You need to put a filter capacitance here so that this L and C together will handle the chopped input current and you will get a reasonable DC voltage here. And now when you turn on the switch, this capacitor has to be charged from 0 volts to Vin. So that will give rise to an inrush current. So in the case of boost, it is the output capacitor charging that gives rise to the inrush current. And here it is the input capacitor charging that will give rise to an inrush current. The problem is unlikely to be as severe as in the boost converter case, but it still exists. If you have any opinions or experience in this matter regarding relative inrush current between boost converter versus buck converter, please post your opinion here in the discussion forum. So the next question is, will the switch help? You can guess. It's a shunt switch. It's unlikely to help. Let's see the inrush current with the switch operating. Let's keep the duty cycle at 0.4 and start the circuit. We can do a simulation again using LT spice. This is the inrush current with the switch switched off, that is D equal to 0. Now let's keep the duty cycle at zero point 0.4 and switch on the circuit. Much worse. It goes to 150 amperes. The switch is in the shunt path and there is a boost action also that is taking place, and the input current is much worse. So if you want to avoid this, do not switch on the switch too early. The capacitor voltage, previously it went up to almost 360 volts, and now there is a boost action also, and it just shoots up to 550 volts or so. So the obvious answer to this question, will the switch help or not, is an emphatic no. So what can we do about it? How do we mitigate this problem? One way of doing that is to insert a resistance. It will reduce the current. It will increase the damping. So this resistance is now part of the converter circuit. Notice that the voltage here will dip because of the voltage drop in the resistance. But the voltage here will not dip. So the other equipment will not be affected by this. This can work, but there are some problems. Suppose we leave this resistor in place even during normal operation, then there is obviously going to be power loss and a reduction in efficiency, which is not a good thing. So once the initial transient is over, we can cut off the resistance with a switch, very likely a power semiconductor switch. There are some issues in this arrangement. If you put too small value of resistance, then it won't sufficiently reduce the current. If you put a large value of resistance so that it will reduce the current sufficiently, then the capacitor won't get charged to the full value of 180 volts, but a reduced value, maybe 80 volts. Now if I close the switch, I will have another transient as the capacitor gets charged from 80 to 180 volts. Designing this may be a bit tricky. Now you may have two surge currents, one when the boost converter is powered on and the second when the resistance is cut out. Another way, perhaps a better way, is to insert a power transistor in series. Here it shows a power MOSFET. You can use an IGBT. The power MOSFET has three terminals: drain, gate, and source. Increase the gate to source voltage slowly. The main current between drain and source slowly increases. The device goes through the active region and turns on slowly. That will ensure that the capacitor is charged more slowly and the surge of current is avoided. After a certain delay, the MOSFET is fully turned on. So you can notice both in this and in the previous case, there is a switch that is left on all the time when the boost converter is operating. That will add to the losses in the circuit. The next method, which is a popular method, is to insert an NTC thermistor in series. This is a negative temperature coefficient device. This NTC thermistor is a passive device, so a single component is just inserted. We will see now how an NTC thermistor is helpful in reducing the inrush current. NTC thermistor is made of semiconductor material. NTC stands for negative temperature coefficient. It's a passive component. It is inserted on the input side of a boost converter. The resistance value of this device changes dramatically with temperature. This shows a typical resistance versus temperature plot of an NTC thermistor. The x-axis here is temperature. The y-axis is the resistance of the thermistor. The y-axis is plotted on log scale. You can see that around 25 degrees it is 10 ohms, while at 100 degrees it is less than 1 ohm, and at 150 degrees it is 0.2 ohm, and so on. The idea is very simple. Initially, the temperature is low, the room temperature, 25 degrees, 30 degrees. Because the temperature is low, the resistance is high, it limits the surge current, it limits the inrush current. As the boost converter operates, current flows through this device, the temperature goes up to, let's say, 150 degrees, and the resistance falls. So under normal operating conditions, there is a small resistance in series with your boost converter. But under starting conditions, there is a high resistance in series with the boost converter. That's the idea. It works pretty well. It is a very popular solution, particularly in AC to DC chargers, phone chargers, laptop power supplies. On the input side, you will have a rectifier followed by a boost converter, and the boost converter has the inrush current problem. So you may use an NTC thermistor on the input side of that boost converter. Under normal conditions, thermistor is always left, so there is a small power loss in the thermistor. Not very high, but there is a power loss. The really good thing about this is it's a passive component. If you turn on and turn off this switch too often and do not allow the thermistor time to cool, it may be a minute, then you may not be giving sufficient time for the thermistor to cool, and so a surge of current may still happen and a fuse may still blow. Otherwise, this is a popular solution used in phone chargers, laptop chargers, etc. With this, we have come to the end of this video. In this video, we saw how inrush current surge can occur in a boost converter, what problems it can give rise to, and what solutions can be adopted. Boost converter has a few more problems. In a subsequent video, I'll try and summarize many of the problems associated with the boost converter. Don't get me wrong, boost converter is a very good and popular converter circuit, often used. One has to be aware what problems it can pose to the engineer. If you like this video and this series of videos, please click the like button and subscribe to this channel. You may also wish to share this video with others who may be interested in it. Thank you.